Welcome to our Exam 4 review, Vector Calculus. Let's go ahead and get started. So first off here we are evaluating a line integral along C, and C is a segment from 1, 0, -1 to 0, 1, 2. So remember with line integrals, our line integral here, notice, is with respect to S. Remember with line integrals what you do is you plug in your parameterization. So here ds is the square root of dx dt squared plus dy dt squared, so we'll have to compute that first, and then we plug in our parameterization for our curve x of t, y of t. Now if we knew more about the situation, we would be able to use the fundamental theorem of line integrals. So here, you need a smooth curve, you need which we actually have that, differentiable function, and then the gradient of f is continuous. And in fact, if we go back here and take a look at our situation here, this is a polynomial, and polynomials are always differentiable and continuous. But here we're doing the integral of the gradient of f dot dr. Okay, so the gradient of f, that's fx, fy, dr is dx, dy. Okay, so this is a line integral that's in terms of dx and dy, where ours is in terms of ds. So if it had one of these two forms, we could think about using the fundamental theorem of line integrals, but we're just going to use the definition. Okay, so our ds here is the square root of dx dt squared plus dy dt squared. And so we need to find our parameterization for that segment and then find x of t and y of t. Okay, so our curve C, remember you can always parameterize a segment with convex combinations. That is 1 minus t times that starting point, which is 1, 0, -1. And then plus t times your ending point, which is the 0, 1, 2. And then 1 minus t comes, let's simplify this coordinate wise. So 1 minus t times 1 is 1 minus t plus t times 0. So that first coordinate is just 1 minus t. 1 minus t times 0 is 0. T times 1 is t. 0 and t is t. And then 1 minus t times -1 is t minus 1. Change the signs here. And then 2t. So t minus 1 plus 2t, that's going to be 3t minus 1 in the z-coordinate. And then always when we do convex combinations, our t is between 0 and 1. So our interval is always 0 to 1 there. Alright, so here's our x. X is 1 minus t, our y is t, and our z is 3t minus 1. Actually here in ds, since we've got a three-dimensional curve here, we're going to have to add one more term in here, dz dt squared. Okay, so x is 1 minus t, so just note there then that dx dt is going to be equal to -1 dy dt. Since y is t, dy dt is 1, and then dz dt. Z is 3t minus 1, so dz dt is 3. So let's go ahead and start writing out this line integral. So then the line integral along C of 3y squared plus z ds is going to equal the integral, changing things over to t. Our curve, parametric curves goes from t equals 0 to 1. And then 3 times our y squared, y is t, so that'll be 3t squared, plus z. Z is 3t minus 1, so plus 3t minus 1. And then ds, which is going to be square root of dx dt squared, so that's a negative 1 squared, plus dy dt squared, so 1 squared, and then dz dt squared is 3 squared. And that's dt. So this is just a constant. 9 and 1 and 1 is 11, so square root of 11, we've got a constant that we can factor out in front. And then we'll just be integrating our 3t squared plus 3t minus 1. So that antiderivative then is going to be 3t cubed over 3 plus 3t squared over 2, just using power rule here, and minus t, and we're going from 0 to 1. So 3's cancel here, so just doing a little plug-in here, so we got square root 11, and then plug in 1, we're going to have 1 cubed is 1, plus 3 halves times 1 squared is 3 halves, and minus 1. And if we plug in 0 all the way across, we just get a 0. Okay, so there's our substitutions. 1 and negative 1 cancel. This is just 3 halves root 11. Alright, all set there. Here we're evaluating the line integral y dx plus 2x dy, and c is a portion of the circle here in the lower half plane with positive orientation. Okay, so let's start off by sketching our curve here, and we need to parameterize, and then we'll plug in parameterizations. So this is just a circle of radius 3, and we're looking at the lower half of that circle. So it looks something like this. And let's see, we've got positive orientation, which is counterclockwise, so that curve is oriented like that. That's our C. And remember that you can parameterize a circle with cosine t and sine t, but here our radius is 3, so we are going to parameterize with 3 cosine t, 3 sine t. And then the angle, t is actually the angle, is going to start at pi and go to 2 pi. So this is going to be 0 less than equal, I'm sorry, not 0, pi less than equal t less than equal 2 pi. So here's our x, 3 cosine t, here's our y. So x is 3 cosine t, and our y then is 3 sine t. And we will need a dx and a dy. So then dx is going to be the derivative of 3 cosine t is going to be negative 3 sine t dt. And dy, the derivative of 3 sine t is 3 cosine t dt. And now we're ready to start doing our plugins. So the line integral along C of y dx plus 2x dy is going to be the integral from pi to 2 pi. And then y is 3 sine t, dx is negative 3 sine t, so this is going to be 3 sine t times negative 3 sine t, and then we're adding 2 x dy, so 3 cosine t and 3 cosine t, so times 3 cosine t and another 3 cosine t. And actually, the dx here, there, that had dt as part of it. So scooch this guy over here. dt here and here. So if we do a little bit of simplifying, then this is integral from pi to 2 pi. Here we've got a negative 9 sine squared of t. And here we've got 3 times 3 is 9 times 2, 18, plus 18 cosine squared t dt. So now we're ready to integrate. We could simplify things a little bit here if we wanted to. We could pull out actually a common factor of 9. Let's see, I'm trying to think if that's going to really simplify things enough for us. See, we're going to have to integrate each one of these, we're going to have to use the half-angle formulas. So this is going to turn into a 1/2 times 1 minus cosine 2t. And this will be a 1/2 1 plus cosine 2t. Why don't we go ahead and leave these coefficients in there? You might get some canceling. So integral pi to 2 pi is going to be a negative 9, and then this will be times 1/2 times 1 minus cosine 2t, and then plus 18 times, I guess those extra parentheses here are kind of redundant here. Just put a multiplication in there. 18 times 1/2 1 plus cosine 2t dt. And then let's see here. 2 goes into 18 9 times. So this is going to equal integral from pi to 2 pi. Let's go ahead and collect our like terms. So here we've got a negative 9/2 times 1. And then here we've got a positive 9 times 1, or positive 18/2. So I guess 18/2 minus 9/2 is going to leave 9/2. Then we've got a negative 9/2 times negative cosine 2t is going to be positive 9/2 cosine 2t. And then with this multiplication, we've got a 9, or an 18/2 cosine 2t. Oh, okay, so let's put together our 18/2 cosine 2t with our 9/2 cosine 2t there. So 18 and 9 is 27. So actually have 27/2 cosine 2t. Combine those like terms, because we've got both cosine 2t terms. And now we can do an antiderivative. So here our antiderivative is 9/2 t. And then plus antiderivative here is going to be 1/2 sine 2t times our 27/2 out in front. That'll be 27/4 sine 2t. And that whole thing's getting evaluated from pi to 2 pi. So when we plug the 2 pi in here for t, we get sine of 4 pi, which is 0. When we plug in the pi, here we get sine of 2 pi, which is also 0. So this term isn't going to add anything to the value of the integral. But 2 pi plugged into the 9/2 t, so this will be 9/2 times 2 pi. Minus, and then we plug the 2 pi in here, that's just 0, and then minus 9/2 times pi plugged in there, and then again pi plugged in here gives 0. So this is just 18/2 pi minus 9/2 pi, which is 9/2 pi. So there we have that line integral. Now this one, notice, y dx, 2x dy, these are polynomials, those are continuous. Here, our function f, if we can find a gradient of f dot dr, write this as a gradient of f dot dr, then we could use fundamental theorem on that one also. So in other words, this is our p, and 2x is our q. So first we would need to check, in order to find out if it's conservative, you want to check and see is dq dy, dq dx equal to dp dy, and dq dx is 2, dp dy is 1. Okay, so fundamental theorem of line integrals is not going to work for this one also, because what we need here, remember our test to see that f is conservative right here is either that the curl of f equals 0, or also here, if we have all of our derivatives, our partials, first partials are continuous, and we have nice regions here. Remember that test was dq dx minus, or I'm sorry, equals dp dy. Okay, that was our test for conservative. Doesn't work here. Now we're computing mass and center of mass of a wire. Okay, so remember the mass and center of mass formulas here. So mass of a wire is the integral of the density ds, and then the x-coordinate of the center of mass is 1 over the mass integral x rho. Y-coordinate is 1 over mass integral y rho. And if we've got a curve in space, z-coordinate would be 1 over mass integral of z times rho. Okay, so these are the formulas that we need. Let's go ahead and bring these guys over. Okay, so first we're going to need mass, and then we're going to need our x bar, y bar, and then eventually z bar. Alright, so let's first compute our mass. So our rho here, they give us our x, y, and z. Okay, so they have already parameterized the curve for us, so that part's done, so that's nice. We do need to compute our ds here. Okay, so we're going to need dx dt, dy dt, and dz dt, and then we'll be able to perform this this line integral here. So let's go ahead and move these guys down here out of the way. And then do one more copy of those guys. And we'll change our y to a z, and we'll be set to start. So then z bar is going to be 1 over mass integral of z times rho. And in this problem, I'm really most concerned with setup here. So if you can get these guys set up okay, if you feel good with the mass integral, and then you can get the rest of them set up, and we know the method that we need to use to integrate, then we're okay. Alright, so x of t is sine t, so then dx dt is going to be cosine t. Y is 2t, so dy dt is 2, and z is cosine t, so dz dt is equal to negative sine t. So then this line integral here, our parameterization goes from 0 to pi. So this is going to be integral from 0 to pi. And then our rho here is given to be x minus y. So density depends on both the x and y coordinate, but not the z. And we're just going to integrate rho ds. Okay, so our x is sine t and our y is 2t. So this is going to be sine t minus 2t that we're integrating. And then times ds, which is going to be square root of dx dt squared. So we've got a cosine squared t in there, plus dy dt squared, 2 squared, and then plus dz dt squared, so it's a negative sine t squared, which is the same as sine squared, positive sine squared, dt. And so these guys here sum up to 1. And then 2 squared is 4, so this whole thing is just a square root of 5. So this is actually going to be square root of 5. Let's pull that on the outside of the integral. And then we just got to integrate sine t and 2t. So the antiderivative of sine t is going to be negative cosine t. And the antiderivative of 2t is 2t squared over 2, so minus t squared. And then we are evaluating from 0 to pi. Okay, so if we plug in pi here, so we're going to get square root of 5. And then if we plug in the pi, we get cosine of pi is negative 1. Negative of that is positive 1 minus pi squared. And then if we plug in 0, and then this thing is going to be, we're going to be subtracting negative cosine of 0. Cosine 0 is 1, so I'll be subtracting a negative 1, and then minus 0 squared. So we're just adding 1 here. So this is actually going to be square root of 5 times the quantity 1 and 1, 2 minus pi squared. So there's our mass. So now let's go ahead and set up the integral for x bar. So it's going to be 1 over mass, so 1 over root 5 times 2 minus pi squared. And then we're integrating still 0 to pi. Our ds is the same here. That's square root of 5 dt. Okay, this whole thing is root 5. And now we're doing x times rho. And our rho is x minus y, so this is actually x times x minus y. Or if you want, it's x squared minus xy is what we're integrating. So x squared is going to be a sine squared, so we're integrating a sine squared t, minus xy, so 2t sine t, if we bring that out in front. And then ds, again, is square root of 5 dt. So root 5 and dt. Okay, this root 5 cancels with this one. And then for this integral here, we're going to use the half angle. And then for this one here, we're going to use parts because it's a power times a trig function. So this is going to be parts. U is going to equal 2t, and your dv is going to equal sine t dt. And then remember, parts is uv minus integral v du. Okay, so if you do that work there, then you get negative 3 pi over 2 times the factor out in front, the area, 1 over 2 minus pi squared. So in other words, this integral here works out to be negative 3 pi over 2. So I'll let you do that integration and double check there. Don't be too concerned with the integrations here. On this one, I'm more concerned with setup. And then here, 1 over mass, get that same factor, 1 over root 5, 2 minus pi squared. Integral 0 to pi. And now we're integrating y times rho, so that's going to be y times x minus y. So that's going to be xy minus y squared. So xy is at 2t sine t. And then we're subtracting y squared, so 2t squared, 2t times 2t is going to be 4t squared. And then ds is root 5 dt. So this root 5 again cancels. This integration is parts, and then this one is just a power rule. And if you work out the details here, you've got that factor out in front of 1 over the area with the root 5 missing, so 1 over 2 minus pi squared. And then this integral here, if you do the parts and the power rule, works out to be 2 pi minus 4/3 pi cubed. Okay, and I encourage you to do, maybe one of these integrals and work it out. And then our last one, here this is going to be z times x minus y, which is going to be zx minus zy. So that's what we're integrating. So we got that factor of 1 over the mass out in front, 1 over root 5, 2 minus pi squared. And now we're integral 0 to pi and zx. So zx is going to be a sine t cosine t. And we are subtracting off a zy. So zy is going to be a 2t cosine t. And then again, our ds here is root 5 dt. So for this one here, when we integrate the sine t cosine t, well, our root 5's cancel again. When we integrate sine t cosine t, I see a function and its derivative. So u substitution, u du. And then this one again is going to be parts because it's a power times a trig function. Okay, and if you work through the details there, you get 4 over 2 minus pi squared. So the 2 minus pi squared is this factor here. So this integral up here, that should end up being 4. So work out the details for one of those integrals. Get a little bit of practice with your integration by parts. Okay, next up we are integrating a vector field f.dr. So this is stated a little bit differently than the other line integrals we've done so far. And they specify the vector field two-dimensional, and then they say C is any path from 1, 1 to 2, negative 1. Okay, so that any path is giving you a clue that, this should be, this has got to be path independent if it's going to be any path. And if it's path independent, then we can use fundamental theorem of line integrals. So what we need to do is we need to check that our function has continuous first partials here, because remember fundamental theorem of line integrals, going down here, we want to actually show that our function's conservative, and then we want to rewrite our f as the gradient of some little f, and then we'll use fundamental theorem of line integrals. To check that it's conservative, we can either do the curl of f and see that it's 0, or we can check that dq dx is dp dy, and then also we need our first partials to be continuous. In other words, functions differentiable, and the gradient would end up being continuous. Okay, so first off, our vector field here, F, which this is our P and this is our Q, these two components here are polynomial. Okay, so F has components that are polynomials. Okay, and polynomials are differentiable and continuous. Okay, so this is going to tell us that we're going to have continuous first partials. That was the first part of checking to see if a vector field is conservative. And they need to be continuous on sets that have a certain property, but these are defined on the whole plane. So we're going to have continuous first partials on the whole plane. And the whole plane is an open connected region. So it's a nice region. And then if we check the partial derivative condition, dq dx, so the x derivative of q is 3x squared. And then dp dy, the y derivative of this, is also 3x squared. Okay, so that equals dp dy. And that was the last condition to check that f is conservative. Okay, so we know that f is conservative. That was one of our theorems. In other words, our f equals the gradient of little f. So now we got to find that little f. So remember, we back integrate to do that. So our p is equal to fx and our q is equal to fy. And then we back integrate. So if fx is 3x squared y, then our f, we do the integral with respect to x, because we want to undo that x derivative. So then our f is going to be the integral of 3x squared y dx. So, but then y is a constant, and then you integrate 3x squared, you get 3x cubed over 3. The 3's cancel. This is just going to be x cubed y. But then this is an x derivative. I'm sorry, an x integral. So there could have been some terms in our function f here that were just y terms. And when you took the x derivative, the y-only terms went away and you ended up with the 3x squared. So this could be x cubed y plus some y terms. So there could be some function g of y on the end. And then if fy is x cubed plus 2, then we can recover f by doing the y integral of this. So f is going to be the integral of our x cubed plus 2 dy. So these are both constants with respect to y, so we integrate the x cubed, we get x cubed y, and we integrate the 2, we get 2y. But there could have been some terms left over that are only terms in x, okay, and we'll call those h of x. So there could have been terms in, if this is our expression for f, there could have been some x terms on the end, and when we did the y derivative, this went to x cubed, this went to 2, and then these x terms went to 0. So then if we equate these two expressions here, then our f of xy is going to be, well, we've got the common x cubed y, so that's going to be part of our f of xy. And then our g of y, our y-only terms, that would be 2y. And our h of x, our x-only terms, Well, there's no x-only terms up here, so this would be either a constant or 0. So this would be c or 0 up here. Okay, but if you're going to put a constant on the end of here, so we need the plus 2y. But then if you're going to put a constant on the end of there, when you plug that into the integral and then do the subtraction, that constant's going to cancel out. So we can just take the constant to be 0. So here's our antiderivative. Or I'm sorry, our function f, or potential function. And you can double check when you get done to make sure. If you do the x derivative of this term, it goes to 0. The x derivative here is 3x squared y. Okay, that's right there. If you do the y derivative here, you get x cubed. The y derivative here, you get 2, and that's right there. So we've found the right potential function. So now we can use fundamental line theorem of line integrals, because our vector field f is gradient of f for this function f. So what's fundamental theorem say? Well, it says if you're integrating the gradient of f dot dr, that's f at the ending point of the curve minus f at the beginning point of the curve. Okay, so then, so the line integral along c of the gradient of f dot dr, and gradient of f, that's our vector field, because we know our vector field is conservative. Then this is equal to the function value f at the ending point, 2, -1, minus f at the beginning point, 1, 1. And it's totally independent of path. So that's why we could say any path here. Didn't have to give you a path because all the path integrals are the same. So we just plug 2, 1 and 1, 1 into our function here. So I plug a 2 and a -1 in here and a -1 there. So that's going to be 2 cubed is 8 times our y here is -1. And then plus 2 times -1 would be -2. And then we're going to subtract, plugging in 1, 1. So 1 cubed times 1, which is just 1, plus 2 times 1, 2. So here we've got -8, and then -2 is -10. And then minus 2 more, -12. Okay, so that's the value of our line integral. Oh, wait a minute. Back up the bus here. 1 plus 2 is 3. This is -10 and minus 3. That's going to be -13, not -12. There we go. All right. Next up, we're finding the potential function f for this vector field, so it's a three-dimensional. So same thing we did above, except we've got 3 variables. So here's our fx, x cubed z is our fy, and x cubed y plus 1, that's our fz. So to recover f, we're going to do the x integral of f sub x. So the integral of 3x squared yz dx. So y and z are constants. The integral of x squared is x cubed over 3, and then that 3 in the denominator will cancel this one. So we get an x cubed yz plus there could be some y and z terms in f that got differentiated down to 0. So you got this function g that depends only on y's and z's. And then an equivalent expression for f is to integrate f sub y to get back to f. So we could do the y integral of x cubed z. Okay, well, these are all constant with respect to y, so you integrate a constant, you get a constant times y. So this is also x cubed yz. But then there might have been some other x and z terms in f. that got differentiated down to 0. So there's some other function here, g, that just depends on x and z. So see, if you differentiated this, you got back your x cubed z. If you differentiate this with respect to y, you get 0. So there might be some more stuff. And then the third way to recover f is to take the z integral of f sub z. So do integral of x cubed y plus 1 dz. So x cubed y and 1, those are constants. You integrate with respect to z, you get constant times z. So x cubed yz. And then the antiderivative of 1 is going to be plus z. And then there could be some more terms that are just depending on x and y. So you got another function, we'll call it k, that depends on x and y. So if we went backwards to our fz here, if we took z derivative here, we just get 0. Here's our 1 and here's our x cubed y. So there could be some more terms in there. So now we see what's common here is the x cubed yz. So all these guys together here telling us that our f of x, y, z has got to have a x cubed yz in it. And then this term depends only on z. Okay, these two could have added terms in y and z or x and z. So this z is our h of x z, and it's also our g of x, our g of yz. Okay, so g equals h is going to equal z. So another piece there, plus z. And that takes care of these two functions. And then this k of xy, well, there's, you know, the y, any y terms in here could be part of this. Any x terms in here could be part of this, except that, you know, that doesn't have any x terms in it. So that means that this guy here, this has to just be a constant. Okay. So our k here is equal to a constant, or the easiest constant to take is 0. So that means this is our potential function. And then, you know, just double check. If you do the x derivative of this, 3x squared y, 0. So there's your 3x squared y, 3x squared yz. Y derivative here, you get x cubed z and 0. So that works. Z derivative, x cubed y and 1. X cubed y, 1. Okay, so we got the right potential function. Okay, and that's all we were looking for there. Next up, we are evaluating a line integral again along a triangle, and we're going to do it directly, and then we're going to do it using Green's theorem. Okay, well, so let's first do this directly. Let's sketch our region here. So here's our y-axis and our x-axis. We've got 0, 0 in there, negative 1, 1 right here, and then 0, 3 right there. And then our curve goes from 0, 0 to negative 1, 1. So 0, 0 to negative 1, 1. And then from negative 1, 1 to 0, 3, and then back to 0, 0. Okay, so that's our curve C. And then we'll want to break it up into 3 pieces. Let's call this one C1. Let's call this piece here C2. And let's call this piece here C3. And just a little note, notice here that this has negative orientation because it's clockwise. So that's going to play into part B, Green's theorem. Alright, so let's go ahead and parameterize here. So C1. There's a couple things we can do here. I'm just going to use our convex combination parameterization. So I'm going to do 1 minus t times the start point which is up here at 0, 3. And then plus t times the endpoint, which is down here at 0, 0. So 1 minus t times 0 plus t times 0 is going to be 0 in the first coordinate. And then 1 minus t times 3, that'll be 3 minus 3t. T times 0, 0. So 3 minus 3t in the second coordinate. And then 0 is less than equal t is less than equal 1. So t between 0 and 1. That's always that way if we use the convex combination. Let's parameterize C2 the same way. So C2, since we've got negative orientation, this is a nice way to do it. 1 minus t times the start, t times the end. So this will be 1 minus t times, we're starting at 0, 0. And then plus t times our ending point, which is negative 1, 1. Both of these are 0, so this isn't going to contribute anything. We just do t times negative 1 and t times 1. This is just negative t, t. And again, same domain. 0 less than equal t, less than equal 1. And then C3, same deal. 1 minus t times your start point, which is negative 1, 1. And then plus t times your ending point, which is up here at 0, 3. So 1 minus t times negative 1 is going to give you t minus 1. Change both the signs there. And t times 0 in the x-coordinate there, so that's just going to give t minus 1 in the x. And then in the y-coordinate, 1 minus t times 1 is 1 minus t. And then t times 3 is 3t. So 1 minus t plus 3t be 1 plus 2t, or 2t plus 1. And again, 0 less than equal t less than equal 1. So there's our three parameterizations. And then the line integral here along the whole curve C is going to be the line integral along C1 plus the line integral along C2 plus the line integral along C3. So we're going to add all of those pieces up. So let's compute the individual line integrals. So line integral along C1 of xy dx. So this actually is going to be a closed curve here. And here our x, let's see, we need an x, a y, and a dx. Our x is 0 and our y is 3 minus 3t. So let's just jot here. X is equal to 0. So that means then that our dx is going to equal 0 dt, because you do the derivative times dt. And then our y is going to be 3 minus 3t. Let's go ahead and do these guys here. So our x is negative t. So dx then is going to be negative 1 dt, or negative dt. And then y is going to be t. And then here our x is t minus 1. Dx then is going to be 1 dt, so dx equals dt, and then our y is going to be our 1 plus 2t. Alright, so integral along C1, our x, xy dx is going to be 0 here, times 3 minus 3t, and then times 0 dt. So 0 times 3 minus 3t times 0 dt. Oh, let me move this over a little bit here. So our integral of x, y, dx is going to be the integral from 0 to 1, t equals 0 to 1, of here's x, y, and dx. Oh, actually, I need a 0 dt in there. It's still 0 without that 0 dt, but that is part of our dt. So this is 0, part of our dx, excuse me. So this whole integral is 0. We're integrating 0 from 0 to 1. So you integrate 0, you get a constant, but you can't plug into a constant. So constant minus a constant is just equal to 0. So that part of the integral is 0. Line integral along C2 of xy dx is going to be integral 0, 1, and now we do x, y, dx. So negative t times t, negative dt. Negative t times negative dt. So these two negatives are going to make a positive. We're integrating t squared. We're going to get t cubed over 3. And that's evaluated from 0 to 1. So plug in the 1, we get 1/3. Plug in the 0, we get 0. That integral is just 1/3. Integral along C3 now. It's going to be, again, integral 0 to 1, because we're still 0 to 1 here. xy is going to be t minus 1, 1 plus 2t. So t minus 1, 1 plus 2t, and then dx is just dt. So we just FOIL this out. So we've got first terms t, outer terms 2t squared, inner terms negative 1, and last terms negative 2t. So if we reorganize a little bit here, this will be integral 0 to 1. Our outside terms are 2t squared. Our last terms, negative 2t. And our first terms, positive t. So t minus 2t is minus t. And then the inside terms were the negative 1. Collect in like terms. And this is just power rule. So this is going to be 2t cubed over 3. And then antiderivative of t is 1/2 t squared. And antiderivative of 1 is t. And we are integrating from 0 to 1. 0, we plug in, we get 0, 0, 0. So that's not adding anything. Plug in the 1 here. We are going to get 2/3 minus 1/2 minus 1. And if you do the calculator work there, you get negative 5/6. So we add up all three pieces here. So 0 plus 1/3 and minus 5/6. And this is 2/6 here. Minus 5/6 is negative 3/6, negative 1/2. Okay, so that's part A directly. And then part B, Green's theorem. Let's go ahead and sketch our region again here. All right, and we have negative orientation here. Okay, and Green's theorem applies only on curves with positive orientation. Okay, so this is our curve C. So Green's theorem here, Green's theorem is for nice closed curves and regions D, P, and Q, and then this is positive orientation. Okay, so this is positive orientation. Okay, it's got to be positively oriented in order for it to be equal to this right-hand side. So this curve has negative orientation. So what we want to do is, in order to apply Green's theorem, we're going to do the integral along negative c. Okay, so C has negative orientation. Negative C has positive orientation. So we can apply Green's theorem. And we're integrating x, again, we're integrating xy dx. So this is xy dx. But notice Green's theorem is to integrate something that looks like p dx plus q dy. There's no dy term in here, so we'll just add it on, plus 0 dy. So now here's our p, and here's our q. So then Green's theorem says since this is a positively oriented curve, then we can just change this to the line integral over d, where d now is this region in here. It's the interior of the triangle. And instead we look at dq dx minus dp dy. Okay, so dq dx is 0 minus dp dy is x. So we're just integrating negative x dA. Okay, so again, this is dq dx minus dp dy. So now we just want to decide, do we want to integrate this as a regular double integral now? Do you want to integrate with respect to y first or x? Well, if we integrate on x segments, then we've got two different left and rights. So we want to integrate first with respect to y on a vertical segment like that. So now this function down here, our lower function, hits on the line that goes through those 2 points. Well, this just has slope -1. It's down 1, run 1, goes through the origin. So mx plus b, it's going to be -1x or -x plus 0. So that's just y equals -x. And then this one up here, y-intercept is 3, slope is rise 2, run 1. So that's y equals 2x plus 3. So we are going to integrate -x dy dx from y equals -x up to 2x plus 3. And then we're going to let that segment sweep left and right. It's going to start here at -1 and it's going to end here at 0. So x is going to equal -1 to 0. Alright, so we do the antiderivative of -x with respect to y. Well, this is just a constant with respect to y, so we just get -xy. So this is going to be integral from 0 to 1 in x of -xy. And we're evaluating from y equal -x up to 2x plus 3 dx. So this is just integral 0 to 1. Plug in a 2x plus 3 for y. So that's -x times 2x plus 3. And minus -x times -x. Okay, and those two negatives will make a positive. And this integral is dx. So here we've got a negative 2x squared, a -3x, and another -x. Is that right? No, actually, I'm sorry. -2x squared, and then this is -x squared. Makes a -3x squared, and then here's a -3x. So this is integral 0 to 1, -3x squared minus 3x dx. And that just gives us antiderivatives here. This will be -3 x cubed over 3. So these guys cancel. And then minus 3x squared over 2. And we're going from 0 to 1. So plug in 1, we get negative 1 minus 3 halves. And plug in 0, we get, oh no, I'm sorry. I switched my limits of integration up on us here. Negative 1 to 0, and then I switched them 0 to 1. Okay, so if all of these are negative 1 to 0, negative 1 to 0, negative 1 to 0, okay, and then if I plug 0 in, negative 1 to 0, so if I plug 0 in, I just get 0 minus 0, which is 0. And then if I plug negative 1 in here, negative 1 cubed is negative 1, another negative is positive 1, minus, this minus sign, negative 1 squared is 1 times 3 halves, 1 minus 3 halves. There we go. So 1 minus 3 halves is negative 1 half, a negative of that is positive 1 half. Okay, that's the integral along negative c. Okay, so then this implies that the integral along positive c is equal to negative 1 half. Okay, so you change the direction of the curve here from negative c to positive c. That introduces a minus sign. That was one of our properties of line integrals. And then you see the negative 1 half here agrees with the negative 1 half there. There we go. Okay, next we're using Green's theorem to do a setup only for the area of the interior of this ellipse. So remember that parametric equations for that ellipse we can use instead of cosine t and sine t. You look at the bottom number here, that's 5 squared, so that goes plus or minus 5 in the x direction. This is 6 squared, so it goes plus or minus 6 in the y direction. So if you set this up, if you graph this guy, so it's plus or minus 5 in the x, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 in the y, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So if we graph this ellipse, looks like that. And to get the plus or minus 5 in the x direction instead of cosine t, we want 5 cosine t. And to get the plus or minus 6 in the y direction, we want 6 sine t. And then we're going to let, we want positive orientation here, so that's going to be 0 around to 2 pi. Okay, so because for Green's theorem we want positive orientation. So our c is going to be the curve 5 cosine t, 6 sine t, and 0 less than equal t less than equal 2 pi. And so then area, using Green's theorem, remember we can use any one of 3 different setups here for area with Green's theorem. We can either use x dy, negative y dx, or 1/2 x dy minus y dx. So whichever looks like it's going to be easier. For us, we're just setting up, so why don't we use x dy? So this is going to be the line integral along C, closed curve C of x dy. which for us is going to be integral 0 to 2 pi. And then our x is 5 cosine t. And then our dy, the differential of y, is going to be derivative of sine t is cosine t, so that would be 6 cosine t. Okay, so this is dy. And then times dt. And this actually wouldn't be a hard integral to do. It's just 30 cosine squared, and then you use the half angle on the cosine squared. And that would give us our area. But here we're just setting up, so we're all set. Next up, we're practicing some definitions. Open, connected, simply connected. Remember that open means it doesn't contain its boundary. Like an open interval. So this is open. Connected here simply means that it's all in one piece. And simply connected means every closed curve only contains points that are in the set, and that meant that there could be no holes in the set. So we want to classify each of these regions. So here, x greater than 0 and y less than 0. So in the xy plane here, x greater than 0 would be this region over here. Y less than 0 would be this region down here. And it's strictly greater than, strictly less than, so you're not including the boundary, which is those two half lines there, the positive y-axis and the negative x-axis. So this is going to be open because it's not including its boundary. It's all one piece here, so it is connected. And then there's no holes in this here, so it's also simply connected. Let me abbreviate that as SC. Next up, we've got the set of all points x squared plus y squared less than equal 1 but greater than 0. So if it was equal 1, we'd have the circle of radius 1. So less than equal 1 is going to allow the boundary out there. Strictly greater than 0 just means we're not including the origin. So it's all this stuff that's in between, not including the origin. So that's an open circle at the origin. So it is not open because it includes its boundary out here. So it includes part of its boundary. You could also think of the point 0 as being a boundary point because it's at the inside edge of the set. So although it's not open, it is all one connected piece. So this is connected. But it's not simply connected because if I take any curve that goes around the origin, it doesn't contain all points that are in the set because the origin is one of the points that's not in the set. So this is not simply connected. Set of all xy where y is less than x. So y equals x is a 45-degree line, y less than x is below that. So that is an open region. Doesn't include its boundary, which is the line y equal x. It's all one piece connected. And there's no holes in there, so it's simply connected. And then lastly, x between 0 and 2 including, and y between 1 and 2 including. So if we sketch this, x is between 0 and 2, y is between 1 and 2. That's just a box like that, and it includes its boundary, so it's not open. So if these were strict inequalities, then it would be open, and we do use dashed lines. It is connected though, all one piece, and it is also simply connected, no holes in the region. Alright, let's compute some divergence and curl. So remember that the divergence of a vector field f is del dot f. So you take the x derivative of, here's p, and here's our q, and here's our r. So you take x derivative of p. Remember divergence here. Let's see, where'd we go? Here. Divergence is del dot f. So x derivative of p, y derivative of q, and z derivative of r. dp dx, dq dy, dr dz. Okay, so we need the x derivative of p here. So x is our variable, y and z are constants. So that's going to be, so we're going to do derivative with respect to x of x, y, z. And then we're going to do the y derivative of 2y squared z. So derivative with y, 2y squared z. And then the z derivative of y plus 1. So let's see. So x derivative here, this is a constant times x. You differentiate that, you get the constant yz. Y derivative here, z is a constant, it stays. 2 times 2 is 4y, decreasing the exponent, so plus 4yz. And then y is a constant with respect to z, so z derivative there is going to be 0. And then just combine our like terms, so 5yz. So note this is a scalar function, okay, not a vector function. So divergence is scalar, and then curl of f is your vector, remember. So curl f is the gradient vector cross f. So you do ijk first row, derivatives in the second row, pqr in your third row. Okay, and if you don't mind, let me just copy this guy over. And I'll just take and put R, P, Q, and R in here. So P is XYZ, Q 2y squared z, and then R is y plus 1. Myself a little bit more room here. Alright, so remember how we do this? Take out the row and column for I. Remember the cofactor signs are plus, minus, plus. So take out the row and column for I, so we want the y derivative of y plus 1, which is 1, minus the z derivative of 2y squared z, so 2y squared, and that's times I, and then minus, take out the row and column for j, we want the x derivative of y plus 1, which is 0, minus the z derivative of xyz, which is xy, and that's times j, plus, take out the row and column for k, want the x derivative of 2y squared z, which is 0, because those are constants, minus the y derivative of xyz, so x and z are numbers times y, differentiate, you get the numbers, xz, and that's times k. And then, you know, if we wanted to, we could rewrite here a little bit in component notation, 1 minus 2y squared. Negative of negative xy would be xy, and then negative xz in that last component. Curl of f is a vector. Remember, it's talking about the rotation in fluid flow. And divergence is talking about divergence of fluid flow away from a point. All right, almost there. We want to parameterize a curve here, to a vector equation for parameterizing the surface, which is the part of the parabolic sheet y equals 1 minus z squared to the right of the xz plane. All right, so let's try and sketch here. So here's z-axis, x-axis, y-axis. Okay, x is not included in this equation, so it's independent of x. So we're just looking at the yz plane here. And y is written in terms of z. Okay, so y is acting like our dependent variable, z is our independent. So 1 minus z squared. Well, y equals z squared would be a parabola that opens to the right. Negative z squared would be a parabola that opens to the left. 1 minus z squared is going to be shifted 1 unit to the right. So this is going to open like this. So this is in the yz plane. And then x is left out here, so x can vary. So you can vary in the x direction. So you get this parabolic sheet like that. And we only want the part that's to the right of the xz plane. So here's the xz plane, so we're stopping right here, here, here. We just want what's to the right. So this is the surface that we want to parameterize. So, well, since y is written in terms of z, z is going to be one of our parameters, and then y we write in terms of it. And then we're going to have two parameters here. Since y depends on z, that's going to imply that z is going to be a parameter. And then x is left out. X has no restriction, okay? So x has no restriction, so that's going to tell you that x is a parameter. Okay, so x will be the other parameter. So if we write this as an ordered triple here, not f, our parametric equation r is going to depend on x and z. The x equation, or I'm sorry, the x component is just going to be x. We can vary in the x direction, no restriction on x, so that's one of our parameters. And the y component, y is 1 minus z squared, so this is 1 minus z squared. And then the z component is z, that's our other parameter. Now, while there's no restrictions on x is an element of minus infinity to infinity, no restriction there. We do have a restriction on our z because this is, just to the right of the xz plane. So in other words, the y value here has to be greater than 0. So we need our y, which is equal to 1 minus z squared, to be greater than 0. So bring your z squared over as a positive. 1 is greater than z squared. And that means that z squared, or a z, has to be between 1 and negative 1. Okay, these are the values that when you square them, you get something that's less than 1. Alright, so that's going to be z, an element of open interval -1 to 1. Or you can write it like this, that's fine too. So you need to, this restriction isn't necessary. It's not necessary to write it because there's no restriction there, but this one definitely is necessary. Okay, so that determines our parametric curve. Now you could also, if you wanted to, you could write this in terms of u and v. You could let x be u and z be v, and this would be your r of uv. Okay, but it's a little bit easier. We understand what the variables x and z are represented. Okay, now we're looking. All right, next up we are writing the integral that gives surface area of a parametric surface here. And we've got equations of x, y, and z in terms of u and v. U and v are our parameters. I added on a domain for u and v here. So parametric surface, we are using this formula right here. So that's area of a parametric surface. Let's go ahead and bring that guy over. So if it was a function of x and y, then we'd use this. That was last chapter, but we're doing parametric surface. Okay, so what do we need here? Well, we need our derivatives r sub u and r sub v. Okay, so let's write out our function r here in terms of u and v. So our vector valued function, the x equation is u plus 2v, and the y coordinate is u minus 2v, and the z coordinate here is u squared v. And so we need r sub u. So this is going to be the u derivative in each coordinate. So remember, this is going to be dr du, I'm sorry, not dr, dx du, dy du, and dz du, partials. So the u derivative here, u derivative of u is 1, 2v is 0, so that's going to be 1. U derivative here, 1 again. U derivative here, 2uv times that constant. Do the same thing with the v derivative, so r sub v. So we need v derivatives of each coordinate. So v derivative here is 0, here it's 2. 0, negative 2. And then the v derivative here, u squared is a constant. So derivative of a constant times v is the constant, u squared. Alright, then next up we need to find that cross product, and then finally the length of the cross product. So Ru then cross Rv, we're going to form a matrix, ijk in the first row, u goes in the second row, so 1, 1, 2 uv. Now I need to move this guy down and give myself a little more room here. And then in the third row we've got Rb, which is 2, negative 2 u squared. Okay, so remember our sign pattern here for the cofactors is plus minus plus. So positive I, that gets multiplied by this determinant down here. So u squared minus negative 4uv. So that's going to be u squared plus 4uv. And that's times the I. Minus, that's this minus sign. And then we're going to take out the row and column for j. So 1 times u squared minus 2 times 2uv. So that's u squared minus 4uv times j. And let's see here. Then plus, take out the row and column for k, and we've just got a negative 2 minus 2 there. So negative 4 k. And now we need to calculate the length of that guy. So the length of Ru whoops, cross RV. And this is just the sum of the squares of the components. Square root, sum of the squares. Okay, so square the first component, u squared plus 4uv quantity squared, plus, and then this is really negative of u squared minus 4uv, but when you square it, that negative is going to go away. So we can just do u squared minus 4uv squared, and then negative 4 squared. Plus negative 4 squared would be 16. Okay, so this is what we're integrating. So we're going to do integral, and then it's square root of this guy, u squared plus 4uv, quantity squared, plus u squared minus 4uv, quantity squared, and plus a 16. Our area element here in u and v in our parameters is going to be either du dv or dv du, and we're integrating over a rectangle here, so not going to be a problem. So the u limits go from 0 to 1, so this would be 0 to 1, and then the outer limits are the v limits, 0 to 2, and there we go. So, and this is a setup only. This looks like this would be kind of a wicked integral to actually perform. So, and that is the case sometimes with parametric surfaces. When you're getting surface area, you gotta have a nice setup here with, you know, things like sines and cosines that, you know, make a perfect square underneath here reduced to constants. Up we have a surface integral. So we're trying to do the surface integral of 60xy ds. So our surface S is the boundary of the solid region that's enclosed by a cylinder. X squared plus y squared is 4. The plane z equals 0, and the paraboloid z equals x squared plus y squared. All right, so let's first sketch a region, sketch our surface here. Okay, so z equals 0 is just the xy plane. So it's the xy plane on the bottom. This is a cylinder of radius 2, and then our paraboloid is going to come up. So the cylinder of radius 2 is going to bound it laterally here. So this is x squared plus y squared equals 4 there. And that's going to bound it on the sides. Okay, so the side here is x squared plus y squared equals 4. Bottom down there is just z equals 0. And then we've got that paraboloid inside here. So the paraboloid's the top surface, cylinder on the side, and then the xy plane, the bottom surface. So there's actually 3 surfaces here. So this top one, let's call that S1, and that is z equals x squared plus y squared. The side, the cylinder, let's call that S2. And then the bottom here, with z equals 0, let's call that S3. So we've got 3 surfaces. So the integral over the surface S of 60 xy ds is, we're going to have to break this up. It's going to be the integral along the surface S1 of 60 xy ds plus the integral along surface 2 plus the integral along surface 3. So now we compute each one of these individually. So this is similar to the triangle problem with Green's theorem. So first we need to parameterize our surfaces. Okay, so let's first look at S1 here. So S1 is z equals x squared plus y squared. So if we look at our surface integrals here, if your surface integral is a graph z equals g of xy, and that's what we've got an x squared plus y squared, then you evaluate the surface integral. Your surface area element then is going to be just dz dx squared dz dy squared plus 1 square root dA, and then you plug your parameterization, you plug your x squared plus y squared in for z in your function of xyz. Okay, so that's what we're doing here. So we don't have to do a parameterization here because our function is in terms of x and y for that first surface. So the integral along S1 of our 60 xy ds then is going to be a double integral over domain D, and the domain D is going to be project this onto the xy plane. That's going to be the circle of radius 2, and then this is going to be 60 xy. There's no place to plug in our z equals x squared plus y squared, but then our area element ds in this case is square root of dz dx squared plus dz dy squared plus 1. That's our area element. Okay, and that's right here. So this is going to be times square root. Dz dx squared is 2x, quantity squared. And then dz dy, the y derivative here is 2y, y derivative there is 0, so 2y squared. And then plus 1. And then dA. Okay, so our domain of integration, D here, when we project down, this is just circle of radius 2, right? That's D. And this is a nice region in polar coordinates. And then notice here, this is 2x times 2x, 4x squared. This is 4y squared. Notice that this is 4 times the quantity x squared plus y squared plus 1. So this is r squared. That's nice in polar coordinates. So why don't we change this to polar, or actually cylindrical coordinates, polar with z. And this will be integral. We've got a 60. Our x is r cosine theta. Okay, right here I'm putting in r cosine theta and r sine theta for xy. And then this is going to be 4r squared plus 1 square root. So root 4r squared plus 1. And then dA, we use the polar area element, which is r dr d theta. And then our r is going to go from 0 to 2, inner radius to outer radius. So this is r equals 0 to 2. And then our theta, we revolve that around from 0 to 2 pi. So notice everything's multiplied here, so we can actually separate these integrals out. So we can take the 60 and the r cubed, because you got 3 r's, and the root r squared plus 1. So we got 60 r cubed, and then square root 4r squared plus 1, dr. And then that's going to go from r equals 0 to 2. And then if we take all those constants out, no, I'm sorry, actually here's what we want to do is take our cosine and sine theta, pull them out of the r integral, then this is what's left. and then that's constant with respect to theta. Pull that out of the theta integral. So we can separate it into two separate integrals. And then this will be integral from 0 to 2 pi, and what's left in there is the sine theta, cosine theta, d theta. Okay, so now we just have to evaluate these two separate integrals, and they're multiplied. Well, let's concentrate on this one here, because I see a function and its derivative, so I'm thinking u equals sine theta, and then my du is going to equal cosine theta, d theta. It's all set up for u substitution. So let's leave this first integral, 0 to 2, 60r cubed, square root 4r squared, plus 1 dr. And then this will be times integral. This is u du. And u is equal sine theta. So we got to plug in our 0 here. So sine of 0 is 0. And then put our 2 theta in here into our u. Sine of 2 pi. Sine of 2 pi is also 0. So this is integral from 0 to 0. Area under a function from 0 to 0, that's 0. So this integral is a number times 0 is 0. Okay, so this first piece here, the integral along S1, is 0. Okay, so that worked out nice. What about S2? Okay, well, that's not a function y in terms of x, so we have to parameterize that one. And in fact, we can use sine t and cosine t, or sine theta, cosine theta, right? With a multiplier of 2 because it's radius 2. And then let our z coordinate vary. So that's going to be parametric. So that's this version here. Your surface is given by r of uv is parametric equations in terms of u and v. We'll do ours in terms of theta and z. And here you plug your parameterizations into the function, and then you need the length of ru cross rv. Okay, so first we need parameterization. Okay, so our S2 here. It's our x and y coordinates that are going to depend on theta here. So let's do 2 cosine theta for our x, and then 2 sine theta is our y, and then our z just varies. Okay, so this is our parameterization for S2. That actually is, that's our function r. So let's write that in there. So this is our r, and it depends on theta and z. And so then what we need is we need to, we need to decide our limits of integration here. So theta goes from 0 to 2 pi. So 0 less than equal theta less than equal 2 pi. So one full revolution to sweep out that cylinder. And then the z here goes from 0 at the bottom, we know that here, to 4 at the top, because it's z equals x squared plus y squared is intersecting with the cylinder, but x squared plus y squared on the cylinder is 4. So z equals x squared plus y squared, and x squared plus y squared equals 4. So the z equals 4 is this top plane. Okay, that's at height z equal 4. So this up here is actually at height 4. So we're going to be 0 less than equal z less than equal 4. So there's our parametric surface there. And now what we need is we need those derivatives. Okay, so we need our theta, and we need our z. So this is Ru and Rv. So the theta derivative here, derivative of cosine is a negative sine, so negative 2 sine theta. Derivative of sine is cosine, so that's 2 cosine theta. And the theta derivative of z is 0. And now we do our z derivatives. Z derivatives in these coordinates are 0. That's 0, 0, and the z derivative here is 1. So now we need to find that cross product, and then we need to find its length. So we need r theta cross r z. And so we got I, J, K, and then this is, let me space those out a little bit more. And this will be r theta in the next row and rz in the last row. So negative 2 sine theta, 2 cos theta, and 0. And last row is 0, 0, 1. So we got our plus minus pattern here. So leave out the row and column for I. So we've got 2 cosine theta minus 0. So 2 cos theta. That's our I. Minus, leave out the row and column for J. We've got negative 2 sine theta and then minus 0. So double negative, that's going to make plus 2 cos theta J. And then leave out the row and column for K. These are just zeros. Okay, so plus 0K. So then that means that the length of r theta cross rz is going to be equal to the square root of 2 cosine theta squared plus another, I'm sorry, let's see here. No, I did something wrong. Let's see, what did I do? Well, the second one here. If I leave out the row and column for J, this is negative 2 sine theta times 1. And this negative, this should be 2 sine theta. Sorry about that. So sine theta, there. Okay, and then 2 sine theta, quantity squared, and then 0 squared on the end. Well, this is just 4 cosine squared. This is 4 sine squared. So this is just the square root of, if we factor out that 4 cosine squared theta plus sine squared theta, which is 1. So that's 4 times 1. Square root of 4 times 1 is square root of 4, which is 2. Okay, so this length of this vector is 2. It's a constant 2. All right, so now we're ready to actually perform that integration here. So then the double integral along that surface S2 of 60 xy ds is going to be equal to the integral over our domain. Let's label this domain D1. So it's going to be integral over the domain D2, which is actually going to be the same domain because the x's and y's are restricted inside that domain. So actually, theta between 0 and 2 pi in here restricts our x and y coordinates to be, because we're doing this is an x and y, that restricts our x and y coordinates inside that same domain. It looks like this. Okay, so D2, and then this is going to be 60 xy, and our x is negative 2 sine theta, because here's our parameterization for the surface. So this is our x and this is our y, and then z is just equal to z. So we plug in our parameterization, so 60 times 2 cos theta times y, which is 2 sine theta, and then we're multiplying by that length of that vector. Okay, so we have done this part here, this part here, f of r of uv. So for us this is theta z, so we plugged in the parameterization. Now we multiply by the length of r theta cross r z, and then dA. Okay, so, and then times the length of r theta cross r z is just 2, and dA. Alright, so our domain here, if we draw our domain D2, it's still that circle of radius 2. And this domain is nice in polar coordinates, and our x and y are already written in terms of theta. So we want to do an integral in terms of polar coordinates here. Now wait, hold on a minute here. Back up a little bit. Our domain, our restriction on our domain is theta 0 to 2 pi and z equals 0 to 4. This domain is the domain of the parameterized function. Okay, so actually our domain D2 is not that circle, but it's actually a rectangle. So D2 is theta in the theta z plane, because theta is our u and z is our v. Theta goes 0 to 2 pi, and z goes 0 to 4, and we're integrating on that rectangle. So the value, so then this dA here is actually going to be d theta dz. So this will be integral 60 times 2 times 2 is 60 times 4, 240. Sine theta cosine theta. And then our dA is d theta dz. And then theta is going from 0 to 2 pi. And z is going from 0 to 4. And so this theta integral in here, notice we've got a sine theta, cosine theta, and that's what we had up here again, from 0 to 2 pi. So this integral right here, that's just 0. Okay, we just did one like that. It's a u substitution. U is sine theta, du is cosine theta d theta. So this then just breaks down to the integral from 0 to 4 of 0 dz. And if you integrate 0, you're going to get 0. So the integral along S2, that second surface, is also 0. So that doesn't contribute anything to the integral. So now we just have to find the integral along that last surface, which is an easy surface. It's z equals 0. So then integral along S3 of our 60 xy ds. And now this one, we're back to this form again. Okay, because it's z equals f of xy, but our f of xy is just 0. Okay, so we're going to do a double integral over a domain D3 of 60xy, and then square root dx dz or dz dx squared is 0, dz dy squared is 0, and then we got a 1. This is just 0 plus 1 dA. And then this domain for this function, it's z equals 0, but it was z equals 0, but the restrictions on x and y are that's inside that cylinder. Okay, so this one does have that circle of radius 2 as the domain. So this is our D3. And we want to use polar coordinates on this. We want to switch to polar here and get a circle of radius 2. So this is going to be integral 60, and then x we change to polar, so that's our cosine theta, and then y is our sine theta here, and then this is just 1, so we don't need that, and then our area element is going to be r dr d theta, and then our r is going to equal 0 to 2, and then our theta is going to equal 0 to 2 pi. Okay, like it was up here. So then we can separate the two integrals again, like we did up above. So this will be the r integral is going to be 60 r cubed sine theta. I'm sorry, 60 r cubed dr. So this is going to be integral 0 to 2 60 r cubed dr. So we got that one. And then what's going to be left for the theta integral, if we pull this sine theta, cosine theta out into the theta, this is what's left for the r. And then the theta integral is going to be integral 0 to 2 pi. And we're going to have another sine theta, cosine theta, d theta. We've seen that integral twice already. This integral is 0. Okay, and this is 0. So all three of these pieces are equal to 0. So the integral along S3 is equal to 0, and so the total surface integral is 0. Oh, all that work for 0? Really?